system and I can't solve it with my mind. That's okay, just listen.
You look comfortable.
Why, thank you. It's very important to be comfortable while studying.
What are you working on?
Just writing some matrices to represent some systems of equations. Have you ever tried it?
No, what would I use that for?
Well, actually, it's very useful for real life. Do you remember the pro shop that we talked about in the last video?
Nope.
Well, let's go back and look at it again. I'll show you how the pro shop could use matrices to solve systems of equations to help its business.
Well, what do you know about matrices?
In the matrix there are rows. Counting down, here I go.
A country club pro shop sells 3 types of women's clothing. We are given a table showing the store's sales of each type of clothing. We also know the price of each type of clothing. Using that information, we can calculate the total sales by using a sum product. We later learned that we could do the same thing for sales over the course of weeks or months by placing the data into matrices and calculating the dot product. Now let's say the manager of the store was considering raising the prices of each item, but he didn't want to just choose random numbers. He wanted to evaluate this intelligently, examining several different options and their financial impact before making a choice. So he created a model to evaluate how much his profit would have increased over the last month based on various price points. He took the original prices of each item and replaced them with variables.
What the manager has actually done here is set up a system of equations. Let's examine the process in detail, but using a more simple matrix.
Recall that the dot product means to multiply each row of the first matrix by each column of the second. So this example simplifies into 2 expressions. Now if I had an equal sign, this actually creates 2 equations, aka a system of equations. Notice that the first matrix contains the coefficients of the 2 equations. The second matrix contains the variables, and the third matrix on the other side of the equal sign contains the constants.
So there's the basic idea of setting up equations in matrices. This is actually pretty useful when we want to do it the opposite way around. Let's say that we have the system of equations and we want to solve it using matrices.
First, I'm going to take the coefficients and put them into a matrix. There are 2 variables and 2 equations, so it'll be a 2 by 2 matrix, and that matrix will contain the coefficients of the system. Remember, a coefficient is the number in front of the variable, which is multiplying it. The first column will represent x, the second column y. The variables themselves are not part of this matrix, but I'm going to leave them there for a second so that you can see where these numbers are coming from. With that first x, the coefficient isn't written, but it is the invisible 1, because x is the same as 1 times x. The second matrix is the variable matrix, and the third is the constants.
That was a lovely example, but I could already solve that system by hand. Let's look at a more complicated one where maybe it would be a lot easier to solve it using matrices. In this next example, we have 3 equations and 3 variables.
This one is pretty tedious to solve by hand. So seeing this off the bat, I think the fastest method to solve this might be to use matrices. I'm going to write this system as a product of matrices. There are 3 equations and 3 variables. I'm going to start with a 3 by 3 matrix. The first column will represent x, the second column y, and the third column z. Again, the x, y, and z are not part of the matrix, but I'm just putting them there so that you can see where the numbers are coming from. I put the coefficients of the first equation into the first row, then the second equation into the second row. X is the same as 1x, so the coefficient is 1. Minus y is the same as plus negative y, so the coefficient is negative 1. Notice the second equation has no z, so there are 0 z's. I can put a coefficient of 0 into the z column.
Sometimes we'll see matrices placed into what's called an augmented matrix. Augmented, the vocabulary word, just means to make bigger.
I make the matrix bigger by adding an extra column on the right side, but this column is separate from the others, separated by a bar, and its purpose is to contain the right side of the equation, so think of the bar like an equal sign. My first equation says there are 2 x's, 3 y's, and 1 negative z, and they add up to make negative 1. So this augmented matrix right here represents the same system of equations that we started with, just in different notation.
Let's go back to the first system and talk about how we would solve that system.
There are actually two ways to solve this equation. I could solve by dividing, or I could accomplish the same thing by multiplying by 1/8. That's exactly the trick we're going to use for the matrices. Instead of dividing, we're going to multiply by the inverse
whenever
matrix.
a variable is being multiplied, I solve for that variable by doing the inverse operation, which is dividing. Here's the thing about matrices. I can't divide them. But do you remember that other phrase I used? Inverse operation? That we can use.
Look at this matrix equation where we want to solve for x. With normal variables, you would divide both sides by a. As I said, though, we can't do that, but we can accomplish the same thing by multiplying by the inverse of a.
The matrix. Thinking about communication, mathematical notation. First the two and then...
Notation for inverse is a superscript of -1. With that equation up there, a is your coefficient matrix, x is the variable matrix, and c is the constant matrix. So when you solve for matrix x, you've solved for all the variables.
In this video, I'm not going to go into how to calculate the inverse of a matrix, but we are going to briefly talk about how to use it to solve a system.
Of course, the first thing I need to do is edit my matrices. I'm hitting second matrix, arrowing over to edit, and the question involved a matrix A and a matrix C, so I'm just going to keep those same names to make it more simple on myself. A was a 2 by 2 matrix, so I'm entering that. Going back to edit matrix C, which is my constants. Matrix A is my coefficients. Okay, now the way that we said that we are going to solve this is taking the inverse of A. So I'm going to go in second matrix, select matrix A. I did the inverse using the same button that I used for matrix. And then I'm multiplying that by, again, selecting matrix B. Notice that if I put this in the wrong order, it comes up with an error because it's a dimension mismatch. And we can also try to use division, and you'll see what happens. If I take C and divide by matrix A, the calculator won't let you do that. That's why we need to use the inverse.
There are actually many ways to solve systems of equations using a matrix, but this is the most relevant for our purposes because we can easily use the TI-84 for the inverse method. If you found this video helpful, make sure to hit like and leave a woohoo in the comments area. Have a mathemagical day.
Woohoo!
Look, I got a system and I can't solve it with my mind. That's okay, just listen. Right now it's matrix time. I take the coefficients, put them all in a row.